Welcome to the fascinating world of set theory. Set theory is a fundamental branch of mathematics that deals with the study of sets, which are simply collections of distinct objects. These objects can be anything, numbers, people, or even abstract concepts. Understanding sets is essential because they form the foundation for many areas of mathematics, including algebra, calculus, and logic. In this video, we'll explore the core ideas of set theory, starting with what sets are, how we describe them, and why they matter. Let's begin our journey by defining what a set is and looking at some everyday examples. Set is a well-defined collection of distinct objects called elements or members. For example, the set of primary colors can be written as red, blue, yellow. Each item inside the curly braces is an element of the set. Sets are usually denoted by capital letters such as A, B, or C. The elements can be anything, numbers, letters, or even other sets. The key is that each element is unique within the set, no repeats allowed. This simple idea helps us organize and classify information in a logical way. Objects within a set are called elements or members. If an object belongs to a set, we say it is an element of that set. For example, in the set A equals 1, 2, 3, the number 2 is an element of A. We use the symbol to indicate membership. So we write 2A. If an object is not in the set, we use the symbol. This simple notation allows us to quickly express whether something is part of a group or not, which is very useful in mathematics and logic. There are two common ways to describe sets: roster notation and set builder notation. Roster notation lists all the elements inside curly braces like B equals a EIOU. Set builder notation, on the other hand, describes the properties that define the set, such as C equals X is an even number less than 10. Both notations are useful, depending on whether you want to list elements explicitly or describe them by a rule. Understanding these notations helps you communicate mathematical ideas clearly. Sets can be classified as finite or infinite. A finite set has a countable number of elements like the set of weekdays: Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday. An infinite set, on the other hand, has elements that go on forever, such as the set of all natural numbers: 1, 2, 3. Recognizing whether a set is finite or infinite is important, as it affects how we work with and analyze the set in mathematics. Empty set, also known as the null set, is a set that contains no elements at all. It is denoted by the symbol or by empty curly braces. For example, the set of all square circles is empty because no such object exists. The empty set is unique. There is only one empty set in mathematics. It plays a special role in set theory, serving as the foundation for building more complex sets. Universal set is the set that contains all objects or elements under consideration for a particular discussion. It is usually denoted by the symbol U. For example, if we are talking about the set of all students in a school, then the universal set is the set of all students at that school. The universal set helps us define other sets and their relationships, such as subsets and complement. Subset is a set whose elements are all contained within another set. If every element of set A is also an element of set B, then A is a subset of B, written as a B. For example, if B equals 1, 2, 3, 4 and A equals 2, 3, then A is a subset of B. Subsets are important because they help us compare and relate different sets in mathematics. Proper subset is a subset that contains some, but not all, elements of another set. In other words, if it is a proper subset of B, then a B, but a not equal to B. For example, if B equals 1, 2, 3, then A equals 1, 2 is a proper subset of B. Proper subsets are useful for distinguishing between sets that are exactly the same and those that are only partially similar. Power set of a set is the set of all possible subsets, including the empty set and the set itself. For example, if S equals a B, then the power set of S is a B. The power set is important in mathematics because it helps us understand all the ways elements can be grouped together. The number of subsets in a power set is 2n, where n is the number of elements in the original set. Cardinality refers to the number of elements in a set. For example, the set D equals 2, 4, 6 has a cardinality of 3 because it contains 3 elements. Cardinality is a simple yet powerful concept that helps us compare the sizes of different sets. For infinite sets, cardinality can be more complex, but for finite sets, it's just a matter of counting the element. Two sets are equal if they have exactly the same elements, regardless of the order in which the elements are listed. For example, 1, 2, 3 and 3, 2, 1 are equal sets. The order of elements doesn't matter in sets, only the membership does. This property makes sets different from lists or sequences where order is important. Venn diagrams are visual tools used to represent sets and their relationships. Each set is shown as a circle, and overlapping areas represent elements shared by sets. Venn diagrams help us visualize concepts like union, intersection, and difference, making abstract ideas more concrete. They are widely used in mathematics, logic, and statistics to illustrate how sets interact. Union of two sets, written as AB, is the set of all elements that are in A and B or in both. For example, if A equals 1, 2, 3 and B equals 3, 4, 5, then a B equals 1, 2, 3, 4, 5. The union operation combines all unique elements from both sets, helping us see the total collection of items. Intersection of two sets, written as a B, is the set of all elements that are in both A and B. For example, if A equals 1, 2, 3 and B equals 3, 4, 5, then a B equals 3. Intersection helps us find common elements between sets, which is useful in many areas of mathematics and logic. Difference of two sets, written as a minus B, is the set of elements that are in A but not in B. For example, if A equals 1, 2, 3 and B equals 3, 4, 5, then a minus B equals 1, 2. This operation helps us identify what is unique to one set compared to another, which is useful for filtering and comparison. Complement of a set A, written as A, is the set of all elements in the universal set that are not an A. For example, if the universal set U equals 1, 2, 3, 4, 5, and it equals 1, 2, then the complement of A is 3, 4, 5. Complements help us understand what is outside a particular set within a given context. Disjoint sets are sets that have no elements in common. For example, the sets 1, 2, and 3, 4 are disjoint because they share no elements. Disjoint sets are important in mathematics because they help us identify groups that are completely separate from each other. A singleton set is a set with exactly one element. For example, 7 is a singleton set. Singleton sets are useful for highlighting individual objects or cases in mathematics. They are the simplest non-empty sets and often appear in proofs and examples. Ordered pair is a pair of elements written in a specific order, usually as a B. Ordered pairs are important in set theory because they allow us to define relations and functions. The order matters. A B is different from B, A unless A equals B. Ordered pairs are the building blocks for more complex structures like Cartesian products. Cartesian product of two sets A and B written as A times B is the set of all ordered pairs of B where A is in A and B is in B. For example, if A equals 1, 2 and B equals xy, then A times B equals 1x, 1y, 2x, 2y. Cartesian products are used to define relations and functions between sets. Relation is a set of ordered pairs showing how elements from one set are related to elements of another set. For example, the relation is less than on the set 1, 2, 3 can be written as 1, 2, 1, 3, 2, 3. Relations are a key concept in mathematics, forming the basis for functions and other structures. Function is a special type of relation where each element in the first set is related to exactly one element in the second set. For example, the function f(x) equals plus 1 on the set 1, 2, 3 gives the pairs 1, 2, 2, 3, 3, 4. Functions are essential in mathematics, connecting inputs to outputs in a precise way. Domain of a function is the set of all possible inputs, while the range is the set of all possible outputs. For example, if f(x) equals x2 and the domain is 1, 2, 3, then the range is 1, 4, 9. Understanding domain and range helps us see how functions map elements from one set to another. Subset notation uses symbols to show relationships between sets. The symbol means is a subset of, while means is a proper subset of. These notations help us quickly express how sets are related and compare their contents. Set membership notation uses the symbols and to indicate whether an element belongs to a set. For example, 3, 1, 2, 3 means 3 is in the set while 4, 1, 2, 3 means 4 is not. This notation is fundamental for expressing ideas in set theory. Set operations include union, intersection, difference, and complement. These operations allow us to combine, compare, and manipulate sets in various ways. Mastering these operations is key to understanding more advanced topics in mathematics and logic. Set theory is not just abstract mathematics, it has many real-world applications. It's used in computer science for database design, in logic for reasoning, and in probability for calculating chances. Understanding sets helps us organize information, solve problems, and make decisions in everyday life. In computer science, sets are used to manage data, search for information, and design efficient algorithms. For example, sets help in removing duplicate entries from a list or checking if an item exists in a database. Set operations make these tasks faster and more reliable. Set theory is essential in probability where events are treated as sets. The union and intersection of events help us calculate the likelihood of different outcomes. For example, the probability of either event A or event B happening is related to the union of their sets. In logic, sets help us formalize statements and arguments. Logical connectives like and, or, and not correspond to set operations like intersection, union, and complement. This connection makes set theory a powerful tool for reasoning and proof. We use sets in everyday life often without realizing it. For example, when organizing a playlist, you might group songs by genre. Each genre is a set. When shopping, your cart is a set of items. Recognizing sets helps us organize and manage information more effectively. Russell's paradox is a famous problem in set theory. It asks, does the set of all sets that do not contain themselves contain itself? This paradox showed that naive set theory could lead to contradictions, prompting mathematicians to develop more rigorous foundations for set theory. To avoid paradoxes, mathematicians created axiomatic set theory, which is based on a set of rules or axioms. These axioms define how sets behave and interact, providing a solid foundation for mathematics. The most common system is called Zermelo-Fraenkel Set Theory, often with the Axiom of Choice. Zermelo-Fraenkel Set Theory, abbreviated as ZF or ZFC, with the Axiom of Choice, is the most widely used system for formalizing set theory. It provides a list of axioms that avoid paradoxes and allow mathematicians to build all of mathematics from sets. The axiom of choice is a controversial but important principle in set theory. It states that given any collection of non-empty sets, it's possible to choose one element from each set, even if there's no explicit rule for making the choice. This axiom has far-reaching consequences in mathematics. Infinite sets can have different sizes or cardinalities. For example, the set of natural numbers and the set of real numbers are both infinite, but the set of real numbers is larger in a precise mathematical sense. This idea was developed by mathematician Georg Cantor. A set is countable if its elements can be matched one-to-one with the natural numbers. The set of integers is countable, but the set of real numbers is uncountable. This distinction is important for understanding the different types of infinity in mathematics. Set theory is the language of modern mathematics. It underpins nearly every branch from algebra to calculus to topology. By understanding sets, mathematicians can describe and analyze complex structures in a unified way. Scientists use set theory to classify objects, analyze data, and model relationships. For example, in biology, sets can represent groups of organisms, while in physics, they can describe possible states of a system. Set theory provides a common framework for scientific reasoning. Philosophers use set theory to discuss concepts like identity, existence, and classification. Set theory helps clarify debates about what it means for something to belong to a group or category, making it a valuable tool in philosophical analysis. Set theory is taught in schools as a foundation for mathematical thinking. Learning about sets helps students develop logical reasoning, problem-solving skills, and a deeper understanding of mathematics as a whole. Logic puzzles often use set theory concepts such as grouping, exclusion, and intersection. Solving these puzzles helps sharpen your logical thinking and gives you practical experience with set operations. Set theory is a powerful and versatile branch of mathematics. It provides the language and tools for organizing, comparing, and analyzing collections of objects. From basic definitions to advanced concepts, set theory underpins much of modern mathematics and has countless applications in science, technology, and everyday life. Now that you have a solid understanding of set theory's core concepts, you're ready to explore more advanced topics in mathematics. Whether you're interested in logic, probability, or computer science, the ideas you've learned here will serve as a strong foundation for future learning. Keep exploring and you'll discover just how far the concept of sets can take you.